Hello and welcome to the 30th Course Media Tea Time Talks. It's our first session in 2022. We are part of the InterPore Academy. My name is Mohammed from University of Oslo and I am your host today. Also accompanying me in the studio, Marcel Moura from University of Oslo, Core Lab, and also Nora Brando from Federal University of Oberlandia. Course Media Tea Time Talks are a platform for young and early career researchers to present their work to the broad scientific community worldwide. The Cross Media TTT aims to act as a complementary platform to already very successful geoscience and geoenergy webinars, which is organized by Hadi and Sebastian. Before starting, I would like to thank Tom Boltrace and Maya Rucker, two co-founders and co-organizers, and also Ariane Massini, a co-organizer of PMTTT, that they are no longer with us, and we deeply appreciate all their time, energy, and inputs for the success of Cross Media TTT initiative. Now, let's introduce our first speaker today. Haiyang Zhang completed his master's in petroleum engineering department at Khalifa University and now conducts his doctoral research in their PhD program in Abu Dhabi. Haiyang joined the MSc program in June 2019 after finishing his BSc in petroleum engineering from China University of Petroleum in East China. His research interest is related to digital rock physics. Today, he will give a talk on upscaling of permeability from tomographic images of carbonates. Haiyang, thank you for joining us today, and the floor is yours.
Okay, thank you. Thank you very much for your introduction. Okay, hello everyone. My name is Haiyang, and I'm a PhD student in Khalifa University. I'm very glad to have this opportunity to give a presentation. The title is Carbonate Rock Permeability Upscaling from 3D Tomographic Images, a modified remolation method. Okay, yes. Here's a short introduction to permeability upscaling. There are several upscaling methods, and here I will briefly introduce numerical simulation and renormalization methods. Suppose that we have already know the permeability of each fine cell, Kij. For the numerical simulation, we calculate the pressure and flow rate of each fine cell, and then we can have the total flow rate. Therefore, the upscale permeability or effective permeability can be determined by Darcy's flow equation. But the renormalization methods gives an analytical expression to calculate the effective permeability. For example, the effective permeability of these four blocks can be calculated by King's solution, expressed in this equation. And we will use the 3D renormalization methods in our study. Here's the rock samples. Here's the rock sample. We select silver dolomite, orbiting for carbonate, and total carbonate. As this figure shows, the resolution we selected 13.24 micrometers for SD, 0.81 for A4, and 0.94 for TC. And the below figures are the micro CD images for the three samples. We conduct laboratory measurements on these three samples, such as mercury injection capillary pressure test, and we have the MICP porosity, or we can see the connective porosity, and we have the total porosity and the plug permeability. These are the pore through size distribution curves for these three samples. From the left figure, the pore through size SD the pore through SD is mainly between 1 micrometer and 35 micrometer. And the pores through size with radius 10 micrometer are dominated. For A4 sample, smaller pore through size and wider pore through size distribution, which lies between 0.01 micrometer to 5 micrometer are found, while TC sample has the widest pore size distribution, ranging from 1 nanometer to 40 micrometers, and more peaks can be clearly observed from the distribution curve. So we extracted subsamples from the original three sets of the images, and below table shows the properties including the image size, the resolution, the porosity. Then we use the interactive thresholding method to segment the images. The first three images are the segmented images, where the black represents the pore space and the white are the solid faces. And the last three images are the 3D visualization of the selected domains, where the blue color represents the connected pore space and the green color represents the unconnected pores. This is an introduction to one of the renowned methods, which is proposed by Carver and Carpenhoff, with terminated KRM. To calculate the permeability of the whole block, they divided it into 8 parts, and each part has a non-zero permeability. There's 2 combination ways for configuration A. The permeability is calculated by the first equation, which is the lower bound of permeability. And for configuration B, they use this equation to calculate the upper bound permeability. And it is believed that the equivalent permeability lies between the upper and the lower bound. So they take the square root of the product of these 2 bounds. Based on the KRM, we split the samples into 8 parts, and the pore network model was extracted from each part to calculate the permeability. And the permeability of the whole sample was also calculated. The first table shows these values, and we use those equations to calculate the lower bound, upper bound, and the equivalent permeability. Of course, we have the direct permeability, which are the ground truth, and we calculate the relative errors. So you can find that the relative errors are high, which are around 40%. The relatively high relative errors are caused due to the fact that the direct permeability does not lie between the lower bound and upper bound, and the same problem can be found if we use the data in the study below. So we are thinking, can we find the description of the equivalent permeability and the true permeability? This means that we need enough data pairs to gather the relationship between these 2 values, and we propose a regression-based random methods, and we terminate RKRM. Here's the workflow. We firstly calculate the equivalent permeability using the KRM, and we select the subsample and calculate the equivalent permeability and the direct permeability, like the red cube. And then we slide to a new position and select the second subsample, like the green cube. And we calculate the same data. So the whole sample will be scanned and covered in 3 directions, and several data points will be obtained, like K1, KU1 to KUN. So we use these n data pairs to generate the linear relationship between the KE and the KD, and we have the K equivalent, the equivalent permeability of the whole sample, and then we use this linear relationship to calculate the direct permeability, and we compare the results with the ones obtained by the laboratory measurement or the numerical simulation. For example, if the rock sample size is 500 and the subsample size is 440, and the step size is 20, so we can have 64 values of the KE and KD. Here's the results for the 3 samples. The x-axis is the equivalent permeability, and the y-axis is the direct permeability. So you can find there's a kind of linear relationship between these 2 values. So now we have the KRM equivalent permeability, which is calculated by those equations. And now we use this new equation, the regression equation, to calculate the RKRM regression permeability. And we have the direct permeability. So we compare the relative errors. So you can find there's improvement on the currency. And then this upscaling approach method was applied for the 4th size sample. Because of the 4th size sample, it is cylindrical. This kind of shape cannot be used for calculation. So we select a cuboid as big as possible from the original samples. This table shows the original size and the selected size. So similarly we slide the samples, but in the direction, and get this regression curves. X-axis is the equivalent permeability, and y-axis is direct permeability. And we also calculate the each parts of the whole full size sample, and calculate the permeability of each part. And this table shows the results. So we use the original match method equation to calculate the equivalent permeability, and use the regression equation obtained in last slide to calculate the regression permeability, and compared with the experimental permeability. So you can find that the relative errors are low. There is increase on the estimation accuracy. Finally, is the conclusions. The regression equation, which relates to the equivalent and the direct permeabilities, is obtained using the 64 subsamples for each stroke. The results indicate that the upscale permeability using the regression equation are in good agreement with the ones obtained directly from the whole sample. And the proposed method is then employed to upscale the permeability on fossil carbonate rocks. The upscale permeability corresponds to approximate to the values measured in the laboratory with a maximum error of 11%. This suggests the occurrence of this method. That's all. Thank you. Thanks for listening.
Thank you very much, Haiyang, and I welcome the audience to type in the questions on the field if you have any. I have a quick one myself first.
Yes.
You have a very big spread on the permeabilities according to the subsamples, right? Like for instance, on there, or there's a couple of tables where that you had.
Yeah.
No, I mean like for a same sample, but the subsections inside. Go to the next one, please.
This one.
Next one. Next. Next. Yeah. There, for instance, this subsample 6 and subsample 1, for instance, on the third line of the TC.
Yes.
So this very large spread, is this like by chance you just selected like one point that was super tight in the sample? Or could you just explain what's the reason for this very, very large spread?
Yes. Actually, we split it into the parts and calculate the permeability. This is a permeability for each part. But because of I think it is because of rock heterogeneity that causes the high spread of the permeability, and also this high permeability contrast. Because that's why the original Renard method doesn't work for our samples, because the Renard method is sensitive to the permeability contrast, and that's why. Yeah.
All right.
Yes.
Excuse me, just complementing Marcel's questions. It's something related to that. It's how can you ensure that you are working in a representative region of your sample, as it has a big heterogeneity?
Yes. For this part, let me firstly show this one. For this size, we chose 600. It is not our It is not our REV, because we just want validate the performance of our method on this small size. And then we use this method for the full size samples. And now because we need to select a subsample and slide. And actually we did the REV analysis, and we found that the REV cannot be defined because of the rock heterogeneity. That's what, so we chose so we only slide our sample in this direction. That is the big. We chose the biggest volume, in this direction. That's why we just have several, like 5 to 8 data points in these figures.
Yes, I got it.
Yes.
And what type of rock are you working?
It's carbonate.
Carbonate. Okay,
So,
great. Okay, thanks.
Wonderful. And I have 2 questions of my own. The first one is about the resolution of imaging. Is it, do you see any sensitivity when you, for example, consider submicron resolutions, or you coarsen up your voxel size? Do you see any difference? And the second one, since you are working with carbonates, and in carbonates we often encounter tight rocks, do you think the same method can be applied for the tight carbonate rocks when you have heterogeneity or anisotropy? So it means that the properties change from one place to another place, and also you have different properties in different directions. Thank you.
Yes. Okay. So the first question about the resolution. The resolution selected, you say it's around 13 micrometer. They say it's around 1 micrometer. So if you look at this pole size distribution, you can find that, for example, for SD, the dominant pole size is around, I can see it's slightly bigger than 10 micrometers. So our resolution is fine, because it can detect as much the details and for a current calculation. And for E4 and TC, actually, you can find that there's a lot of poles that cannot be detected under that resolution. But actually, that resolution is the highest resolution that we can have. I mean, do not mention the nanoscale or something like that. So this method is about for the tight rocks. I think it could work, because they say it's a sliding process, and it can, you scan the sample and capture the details as much as possible, because it's a sliding process, and it is also I would say that's a curve fitting to find those features and to get the results. I mean, it could work, I think.
Okay, thank you.
Okay, thank you.
Super. So I guess we don't have any other questions for now. So maybe it's time to move on to our next speaker. And this is Ahmed Samir Rizk. He's a master's student at Khalifa University working on machine learning applications in petroleum engineering. He earned a bachelor's in petroleum engineering from Suez University in Egypt. And Ahmed has also 2 years of experience working in the oil industry, and is also an active member of the SPE Young Professionals. So Ahmed, do you hear us now?
Yes, Marcel.
Okay, very good. The floor is yours. We hear you well.
Yeah, hello everyone. This is Ahmed Samir. And first of all, thank you, Marcel, for this introduction. Today I'm going to present my work about the machine learning perspective for estimating residual oil saturation from carbonate rock images. The structure of the presentation starts with a background about the research, the motivation behind the research. Then I will go through the workflow of the machine learning, starting from digital images, feature engineering, data spokesman simulation, machine learning. Then we will talk about the results, and finally the conclusion. First of all, why residual oil saturation and why we need machine learning to estimate it? First of all, the residual oil saturation can be defined as a capillary trapped oil after conventional recovery techniques. And it's very important because it evaluates the effectiveness of different recovery stage. It's also important to screen the suitable EOR technique. That's why different methods have been developed to estimate this important parameter, including laboratory measurements and simulation techniques. However, laboratory measurements, which include core flooding and centrifuge, they suffer from different drawbacks. They are expensive, they are time-consuming, they are also limited to specific range of operating conditions. For direct simulation techniques, they have been developed driven by the advancement in X-ray scanners, as well as the advancement in computation power of supercomputers. But these direct simulation methods are very computationally expensive in terms of resources as well as in terms of time. For example, if we want to simulate a cube rock sample of length only 72 micrometers, this takes around 50 hours on 2 CPU cores. However, to reduce this number to 3 hours only, we need around 50 CPUs. And repeating this process for several images is very, very resource consuming. That's why we introduced the machine learning workflow to estimate SOR. So the motivation behind this is that obtaining an accurate estimation of SOR is very essential to screen the best candidate EOR technique. And given that the current laboratory measurements and direct simulation measurements are suffer from different drawbacks, and we believe that machine learning can map the relation between the rock morphology and its initial condition to their respective SOR values. This is because the powerful nature of machine learning algorithms to encode the relation between different parameters. We developed this workflow to estimate SOR in a very efficient and quick way. First, we start with the grayscale image. We do some imaging processing on it, like to segment it, to differentiate between the pores and the grains. Then we take a large number of these images through two processes. First one is feature extraction or feature engineering to extract some features that represents the pore space and the morphology of the rock, as well as we do direct simulation on these samples to know what is the SOR values that we will get under a specific water flooding conditions. We take these values from feature extraction as input labels and the SOR from direct simulation as output labels to the machine learning model. For many samples, we train a machine learning model, we develop it, we test it, and then we use it to make the predictions. To start through the workflow, we first should know what is the digital image, which is a building block of this research. The digital image is made of picture elements called pixels or voxels in 3D. And this pixel or voxel contains a number of numbers that represent its color intensity. And we use the micro CT imaging technique. This technique uses X-rays to see inside the objects. It captures series of 2D slices at different projection angles. Then they stack them together to obtain the 3D image. The sample which we are working on here is a carbonate rock sample that was captured at a resolution of 0.48 micrometer, which is a very high resolution. And the size of this image is 500 by 500 by 920. Now, to obtain large number of samples that is required to train the machine learning model, we use the same technique as Haiyang described, like we take a cube and this cube goes through this image and extract different heterogeneous of the sample. This cube has the size of 150 by 150 by 150. After this, we have a huge number of samples, like 7,449 samples. These samples then are processed through segmentation to differentiate between the pore and the grains. After this, we do some feature engineering on this sample. First, we calculate the porosity. The porosity can be calculated easily by dividing the number of pore voxels by the total number of voxels. Also, we use a BNM network model that is a simple technique to extract the pore size distribution and the throat size distribution of each sample. This pore network model it simplifies the pore structure into spheres that represent the pores and cylinders that connect these pores together. From this simplified model, we can have an idea about the pore size distribution as well as the throat size distribution. Here is an example of one of the samples of how the pore size distribution and the throat size distribution can be represented for a carbonate image. We also use a PNM model to calculate the permeability of the image. Because of the simplified architecture of this model, we can use or apply Hagen-Poiseuille equation to calculate the flow rate. Then this flow rate is passed to the Darcy law to calculate the absolute permeability of the sample. Of course, this absolute permeability will not be the very accurate permeability of the sample, but it can give an indication about how the permeability of the sample looks like. And that's what we need to explain or explore the morphology of the rock and the different features that can affect the prediction of SOR. We also use a novel technique developed by Al-Ratrout et al. In 2017 to extract the surface roughness of the image, where a mesh is generated to represent the rock surface, then a volume-preserving curvature smoothing is applied, The curvature is measured for each point, and from this curvature, we use an equation to obtain the surface roughness. Here is lattice Boltzmann simulation to calculate the SOR. And why we choose lattice Boltzmann? Because it has been widely described in the literature that this method is accurate as it does not simplify the pore structure. And the original theory of it is the cellular automata theory, which represents the fluids as particles interact with each other in a billiard-like collision. And we can define what is called the molecular density distribution function, as the number of particles per unit volume per unit velocity of the rock, of the fluid. And we use a governing equation. It's the Lattice-Boltzmann equation to simulate the evolution of the behavior of this density distribution function with time. And by relating this density distribution function to the macroscopic properties such as fluid density and the fluid momentum, we can obtain the macroscopic flow properties. I'm not sure if you can see the model of the equations, but I will describe as much as I can. We here use a D3Q19 model, which is a three-dimensional model and have velocity or density distribution function in 19 directions. We use also a color gradient model to represent the two phases. This color gradient represents each distribution function of each fluid with distinct color. The one is blue and one is red. Then the total density distribution function is the summation of the density distribution function of each fluid. But we don't use a simple BGK model for the single that is used in the single phase flow for simulating this behavior, two-phase flow, but we use a multi-relaxation time scheme that uses a matrix that can map the density distribution function from the velocity space to the moment space. Here we can see how the experiments are done. First, we start with a small value of SW. Then, with injecting water into the sample, this SW or the saturation of water increases in the sample until it reaches a state or a steady state where with more injection of water, there is no change in the saturation of the water. At this point, we define our SOR and we take this as the value which we need. All of these parameters are passed through a machine learning model for training and testing. The first parameter is, as we said, porosity. Then we have the PN permeability, the pore size distribution, solid size distribution. We have the surface roughness, initial water saturation. We have the porosity profile and the initial water saturation profile as well as the corresponding residual oil saturation for each sample. The machine learning model is a tree-based model which we have used. To understand what is a tree-based model, we have to first understand what is a decision tree. A decision tree is an algorithm that simplifies the data and do the regression or classification task by simplifying the data into the purest possible form. But only one decision tree is not enough to make or to deal with huge problems. That's why we need a combination of decision trees. This combination of decision trees are represented by algorithms like gradient boosting and gradient expost. In this research, we concentrated on the gradient boost method, and we trained the model on the huge amount of data we have. Then we found that a very good correlation between the SOR predicted by Lattice Boltzmann and the SOR predicted by the model have been developed with around 0.98 R square in the training set and 0.87 on the testing set. Of course, if we look here at the part which represents the samples with high SOR, we'll find that many deviations, but this because the limited number of samples that have high SOR values. Here we come to the conclusion. Based on these results, we know that the SOR estimation is very accurate, is very important, and we need accurate and fast way to estimate it, because it can be used in screening different EOR techniques, and because of the limitation of the current simulation techniques like Platts Boltzmann, which require a very huge amount of time or huge amount of resources to simulate an image, we developed a machine learning model that based on 7,449 data points were trained and tested. The gradient boost algorithm showed a high predictive capability with R square of 0.87, and this study finally it serves as a proof of concept, and it can be extended to other rock samples as well as to different water flooding conditions. Thank you. Bye.
Thank you very much, Ahmed.
Thank you.
Do we have any questions in the studio? I have a quick one. How does the wettability enters the picture? Is it one of the parameters that you feed into the model? Perhaps you have shown there already, but I just...
Yeah, it's a very good question. Now we are not interested in defining the wettability of the rock. We have made this model or this workflow as related to only specific case of water flooding conditions. So we have fixed the different water flooding conditions, like the wettability of the rock, the injection rate, the different parameters have been fixed, and we are trying to relate only what will happen if we change the morphology of the rock, what will have if we change the structure of the rock, like the pore geometry, all of these parameters which we are concerned about.
Very nice. And do you think the method could be extended to other quantities as well? So you use the residual oil saturation as being like the thing that you want to predict. Do you think the other quantities could be also predicted in this way?
Yes, of course. I think like we have done this for the residual oil saturation, which is somehow it's a very, very complicated function of the different parameters. I think for other quantities, it can be done. And many research in the literature have been done for estimating the permeability, for example. Also for estimating the pressures after simulation, the velocity field, pressure field. All of these quantities have been done in the literature as well.
Right.
Okay, it's wonderful results, Ahmed. Really interesting. I'm just wondering, after how much training of the machine learning algorithm it would be trained enough to be used for general purpose. For example, you trained it enough so everybody can use, and you come and use your code to calculate residual saturations, brine and oil for their carbonates, for their sandstone rocks. Do you think every time we should tune the algorithm, or after enough training it would be mature enough to present or provide good enough results?
Yeah, it's a very good question and very interesting, because we have trained the model on a very complex geometry like the carbonate rock. So if we want to extend for other rocks like sandstone, this kind of heterogeneity does not exist as well. So I think it can be also extended to this kind of rocks like sandstone and all of this. However, we have to consider different parameters such as the size of the image, the resolution of the image. These are also parameters need to be considered. But I can say that like this workflow can be used as a proof of concept. What have been done on carbonate can be done on other rocks as well.
Exactly. And how far you are from calculating endpoint relative permeability values? Since you have the data for residual oil saturation, so it shouldn't be far for calculating endpoint relative permeabilities. Have you tried it? Any results?
I can say like it's an interesting point to research on, but still this is maybe included in future work as well. Yeah.
Perfect. Thank you.
Thank you very much.
Excellent. Congrats. Thank you very much. Okay, so we move on to the closing of our sessions. I'd like to thank both of our speakers from today. And the next session of the Tea Time Talk is already scheduled for the 1st of March. And we are changing a little bit now. So we're going to have some sessions that will be a bit later than usual in European time. Usually our sessions so far have been like at 10:30 in the morning or 3 in the afternoon. But this one, it's at 6 o'clock in Europe, because we want to start to make the sessions a bit of a more reasonable time for the people in other time zones. So now in the Pacific time zone, it will be 9 o'clock. We have one speaker from there. So the two speakers will be Tingyan Chekai from France and Wei Liu Li from Stanford University from the US. And that will be on the 1st of March, 2022. And with that, I would like to finish the session. Thank you very much once again for joining. We look forward to see you next time. And if you would like to be a speaker, or if you'd like to nominate a speaker, we are always building a list of potential future speakers. So feel free to contact us at porusmediattt@gmail.com. Okay, thanks very much. Bye-bye.